Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Optimization in Civil Engineering. In this course, we are going to learn about the optimization techniques, particularly the solution methods that can be employed to solve engineering problems. As an engineer, we involve in various design and other engineering problems. This course is going to give you the insight how to formulate a particular engineering problem into an optimization problem and solve it using specific optimization solution techniques. In this first lecture, we are going to discuss about the optimization problem and how it can be mathematically represented. We are also going to discuss about the various components of the mathematical representation of optimization problem and classify the optimization problem according to the nature of the objective function and the constraints. We'll briefly discuss the various steps involved in developing the mathematical representation of the optimization problem and the generic techniques to solve an optimization problem. With this, let's start this class and know more about optimization in engineering, particularly civil engineering. Welcome to the first lecture of CE771 Optimization in Civil Engineering. Today I am going to introduce the optimization problems in this class. In the process, we are going to know about the optimization problem, how it is mathematically represented, the various components within the mathematical representation of an optimization problem, the various classifications of the optimization problem, steps involved in developing the optimization problem, and the optimization techniques involved to solve a problem. In our daily life, we do various optimization. For example, hello everyone, welcome to the first lecture of CE771 Optimization in Civil Engineering. Today I am going to introduce the optimization problems in this class. In the process, we are going to know about the optimization problem, how it is mathematically represented, the various components within the mathematical representation of an optimization problem, the various classifications of the optimization problem, steps involved in developing the optimization problem, and the optimization techniques involved to solve a problem. In our daily life, we do various optimization. For example, if we want to purchase something from a grocery store, there could be multiple grocery stores with various price, and these grocery stores could be at various distance. When we go out to purchase our intended product, we try to optimize based on the price and the time we have in our hand. Likewise, as an engineer, in every aspect of planning, design, construction, maintenance of any engineering system, whether it is related to transportation, geotechnical, structural, or any of the civil engineering specialization, we make several decisions. And in this process of decision, our main objective is to maximize the desired benefits or minimize the cost of the system. Now, we can actually enumerate all possible solutions to find the best possible option from a given set of problems. If we want to do that, it takes longer time for a very complex problem, and many times it is not feasible in a short duration and provide a better solution. The other alternative to this is that we can use certain technique which can find the best possible solution by understanding the characteristics of a problem and quickly converge to the best possible solution available. So the objective of engineering optimization is to understand the mathematical characteristics of the problem and converge quickly to the best feasible solution. In a nutshell, we can say an optimization is about finding the best possible solution for a given system. Now here is an example. As an engineer working in an asphalt mix plant which is producing two types of asphalt concrete mix, you are required to find out the quantity of these two types of asphalt so that the profit is maximized. So the first type of asphalt concrete mix, the selling price is 4000 rupees per meter cube, whereas the raw material required to mix and come up with this asphalt concrete mix is rupees 2500 per meter cube. On the other hand, there is another asphalt concrete mix whose selling price in the market is rupees 3000 per meter cube. However, the raw material required for it, the cost is rupees 2000 per meter cube. In a typical day, the demand of asphalt concrete mix altogether, both type 1 and type 2, is 1400 meter cube. Depending on our plant capacity, we know that type 1 mix that can be produced in this plant per day is about 500 meter cube. We also know that whatever quantity we produce in type 1, the quantity of type 2 is at least twice that quantity, if not more. With these constraints and with all these details, how can we find out how much we should be producing to maximize the benefit? This type of problem we get in our everyday work all the time. It is now our interest to find out how we can mathematically transform this particular problem so that we can solve it and get the result. So here is an example how we can represent it. Let's assume the quantity which needs to be supplied for type 1 is x1 and the quantity or the volume which needs to be supplied for type 2 asphalt concrete mix is x2. So if you look into the profit of the type 1 asphalt concrete, it is the difference between the selling price and the material cost. The difference between selling price, which was 4000 rupees per meter cube, and the material cost 2500 rupees per meter cube, we get the difference as 1500 meter cube, and we are supplying x1 meter cube. So the total profit for asphalt concrete mix 1 is going to be 1500 times x1 rupees. Similarly, the profit for type 2 asphalt concrete mix is going to be 1000 x2 rupees. Now in the condition we also said that the maximum amount of asphalt concrete we can produce, particularly the type 1, is 500 meter cube. So we have this condition x1 should be less than 500. Now the other condition we had is that total demand in a particular day is going to be 1400 meter cube or less. So in this case we are representing it as x1 plus x2 less equal to 1400 meter cube. We also said the type 2 asphalt concrete mix production is at least twice of the type 1 asphalt concrete mix production. We need to satisfy that condition and we are indicating it as 2x1 less equal to x2. Our objective is to maximize the profit. The maximization of profit you can represent as 1500 x1 plus 1000 x2, and we also need to satisfy the three conditions, which is x1 lesser equal to 500, x1 plus x2 is lesser equal to 1400 meter cube, 2x1 is lesser equal to x2. So with this condition, if we want to represent the problem, we can represent it as maximize 1500 x1 plus 1000 x2 subject to x1 less equal to 500 and x1 plus x2 less equal to 1400 and 2x1 less equal to x2. Now in this problem, when we represent it, this part of the problem is known as objective function. This part of the problem are known as constraints, and the variables which are there in the objective function such as x1 and x2 are known as decision variables. Not all decision variables are design variables. While developing a problem, we try to use the decision variables which are sensitive, and we try to design or we try to develop the optimization problem based on the highly sensitive decision variables. The decision variables that are highly sensitive and considered in the optimization problem are known as design variables. When we are developing an optimization formulation, we try to identify the design variables and develop the mathematical formulation for that optimization problem. In a generic form, an optimization problem can be represented as this. We can see that an objective function can be either minimized or maximized, and an objective function can have more than one variable. So we can represent the objective function as fx, where x represent all the different variables. Now the constraints which you want to represent, it could be of two different types. Either it could be of inequality constraint, where the constraint is either lesser equal to 0 or greater equal to 0. In this case, we have represented lesser equal to 0. And we can have more than one such constraint. So the J represents the constraint and it could be up to capital J. Similarly, the constraint could be of equality nature, or we call it equality constraint. In this case, the constraint is equal to 0, and we can have more than one such constraints. In this case, you see that we have k number of equality constraints. Now coming to the individual values of the decision variable or the design variable. This design variable can have a minimum and the maximum value as well. So those variables are also can be represented in this format so that it is fully represented. So this goes the generic optimization problem representation. Now we will look into the various classification of optimization problem. So the classification of optimization problem, if you are looking into, it depends on the existence of constraints. An optimization problem without any constraint is known as unconstrained optimization problem. In this type of problem, only objective function exists. There won't be any constraint. Whereas a constraint optimization problem will definitely contain either inequality type of constraint or equality type of constraint. So if we quickly go back to the previous slide where we discussed about the optimization problem, the generic form, in this case we won't have this part in the unconstrained optimization problem. If we have this thing, it looks like the complete problem, which is this, then we call it as a constraint optimization problem. So let's go back to the other classifications. We can have the optimization problem where the design variables could be static or it could be dynamic. If it is static, which means the design variable does not depend on any other value. In certain cases, the design variable may depend on other variable. For example, if we want to design a dam where the catchment area or the place where we want to construct the dam could be location specific, and if we consider the location as one of the input condition for the design variable, then the overall optimization problem of such a problem can be a dynamic optimization, because the solution or the problem is going to change from one location to another. Whereas if we keep it generic, it can become a static optimization problem. Apart from the nature of design variables, there are optimization problem can be classified based on the physical structure of the problem. Sometimes the problem might have more than one stages, and each stage involved requires input from the previous stage. A preceding stage will always influence the succeeding stage of the problem. If we have that kind of system, we call it an optimal control problem. For example, if we want to develop an alignment, first we need to identify the cities through which a road or the rail alignment needs to pass through. So that is our stage 1. In the second stage, once we identify those locations, we need to come up with a corridor through which the alignment is going to pass through. So that becomes your stage 2. Once we identify the corridor that passes through the pre-selected locations, then we can develop the actual alignment or design the alignment within that scope. So that becomes stage 3. If you see in this problem, each stage depends on the previous stage, and this becomes an optimal control problem. If our problem is of not such nature, then it becomes non-optimal control problem. The classification of optimization problem can also depend on nature of the equation involved. For example, if the objective function or the constraint have nonlinear equations, then that optimization problem is known as nonlinear programming problem. Sometimes the variables in the objective function or in the constraint could be the product of each other with a raised power to some order. If we have the problem of that nature, it becomes geometric programming problem.